Today, I am honored to introduce a highly practical and cutting-edge course, Conceptual Design of Mechatronics. In this rapidly developing era, mechatronics technology has become a key driving force for industrial advancement. Next, I will elaborate on the content and value of this course from 4 aspects. The learning objectives of this course are: knowledge objectives. Familiarize yourself with the environment interface of the mechatronics module and master the basic operational processes of the module. Skill objectives. 1. Become familiar with the environment interface of the NX Software MCD module. 2. Master the physical simulation settings for rigid bodies in the NX Software MCD module. 3. Master the settings for fixed pairs, sliding pairs, and hinge pairs in the basic motion pairs of the NX Software MCD module. 4. Master the velocity control settings for actuators in the NX Software MCD module. 5. Master the comprehensive application methods of motion pairs and actuators to achieve adjustments in simulation effects. Let's first introduce the concept of this course. The Mechatronics Concept Design Solution is a newly developed MCD module by Siemens based on NX software. It is a practical mechanical design method suitable for the concept design of mechatronic products. Using the software, 3D modeling and simulation of concepts involving multiple physical fields and automated behaviors commonly found in mechatronic products can be performed. In 2016, Siemens introduced the concept of the digital twin, which creates a virtual model of a physical object in a digital manner. This simulates the behavior characteristics of entities in the physical space within a real environment, achieving precise mapping between the virtual and the real. This provides a new technical solution for managing the entire product life cycle. The MCD module accelerates the development speed of products involving mechanical design, electrical design, and software design disciplines. This includes the conceptual design of mechanical components, sensors, actuators, and motion, enabling innovative design technologies to help mechanical designers meet increasing demands, improve production efficiency, shorten design cycles, and reduce costs. This course primarily focuses on the application of the NX MCD module, involving specific design work across mechanical design, electrical design, and automation design disciplines. You will complete settings based on different case scenarios provided to achieve realistic simulation effects, and to master the basic concepts of mechatronics concept design. This course is primarily divided into 3 stages, with the difficulty of case studies progressing from basic to advanced and comprehensive applications. The design allows you to master the command operations of the NX MCD module through this course, enabling you to independently complete the setup and simulation of simple to medium difficulty cases. Next, we will begin with the software operations of the NX MCD module. First, by using the new command, we will enter the Mechatronics Concept Design interface to create an MCD project file. Open the existing model using the Open command, access the Electromechanical Concept Design interface, and create an MCD project file. The Home toolbar is divided into several groups: System Engineering, Mechatronic Concepts, Simulation, Mechanical, Electrical, Automation, and Design Collaboration. Once the mechanical, electrical, and automation settings are completed, the basic mechatronic objects, motion pairs, constraints, sensors, and actuators will be displayed in the case navigation bar, as shown in the figure. Now, let's look at the specific operational process. First, we focus on the main settings of the MCD module. The simulation in the MCD module is primarily based on the needs for settings of basic mechatronic objects, flexible mechatronic items, motion pairs and constraints, materials, coupling pairs, sensors and actuators, runtime behaviors, signals, and signal connections. 1. Rigid bodies. Create all moving parts as rigid bodies via Home. Mechanical, rigid bodies. 2. Collision bodies. Define the parameters of collision bodies via Home. Mechanical, collision bodies. 3. Object source. Set the parameters for object sources through the drop-down menu under Home, Mechanical, Rigid Bodies. 4. Object collector. Set parameters through the drop-down menu under Home, Mechanical, Rigid Bodies for object source collector. Next, we will look at motion pairs and constraints. 1. Hinge pair. Set hinge pairs via Home, Mechanical, Basic motion pairs. Note that the vector direction is the axis of hinge secondary rotation, and the anchor point is the center of rotation. 2. Sliding pair. Set sliding pairs via Home, Mechanical, Basic motion pairs. Note that the vector direction is the axis of rotating secondary rotation, and the anchor point is the center of rotation. 3. Fixed pair. Create fixed pairs via Home, Mechanical, Basic motion pairs. 4. Screw pair. Set screw pairs via Home, Mechanical, Basic motion pairs. Note that the screw pair restricts only 1 degree of freedom. The object can move freely except along the axis direction. 5. Cylindrical pair. Set cylindrical pairs via Home, Mechanical, Basic motion pairs. Note that the cylindrical pair has rotational and translational degrees of freedom. Spherical pair. Set spherical pairs via Home, Mechanical, Basic motion pairs. Next, we will learn about sensors and actuators. 1. Collision sensor. Define parameters via Home electrical collision sensor. Note that only defined categories will trigger collision events. 2. Transmission plane. Set the plane as a transmission plane via Home, Electrical, Position Control drop-down menu, Transmission plane. 3. Position control. Define position control parameters via Home, Electrical, Position control. Note that the required time equals displacement divides velocity. 4. Velocity control. Set an actuator as a driving element via Home, Electrical, Position control drop-down menu, Velocity control. Note that only motion pairs can serve as actuators. Next, we will learn about simulation sequences. 1. Sequence editor. Add simulation sequences via the toolbar, Sequence editor, right-click. 2. Sequence edit. The sequence editor in the navigator displays all simulation sequences created in the mechanical system for managing when the simulation sequences start executing under any conditions, controlling the states of actuators or other objects at different times. Now, let's study the signal adapters. 1. Signal adapter. Define adapter parameters via Home, Electrical, Symbol table drop-down menu, Signal adapter. Note that using the signal adapter command encapsulates runtime formulas and signals. 2. External signal adapter. Choose PluximADV via Home, Automation, External signal adapter to connect MCD with PLC. 3. Signal mapping. Select MCD signals and external signals via Home, Automation, Symbol table drop-down menu, Signal mapping to perform the mapping. Finally, let's look at the case results. Case 1. The simulation effect can be achieved through the basic mechatronic object settings and actuator settings in the MCD module. Case 2. The simulation effect can be achieved through the basic mechatronic object settings, motion pairs, and actuator settings in the MCD module. Case 3. The simulation effect can be achieved through the basic mechatronic object settings, motion pairs, sensors, actuators, simulation sequence or signal creation and connections, and PLC program control settings in the MCD module. Case 4. The simulation effect can be achieved through the basic mechatronic object settings, motion pairs, sensors, actuators, simulation sequence or signal creation and connections, and PLC program control settings in the MCD module. In this lesson, we have learned about the following content. 1. The role of the NXMCD software platform and an introduction to the commonly used tools in the interface operation toolbar and navigator. 2. An overview of the operating procedures for the NXMCD software. 3. Setting up simulations for mechatronic objects, virtual control, and virtual real synchronization debugging. Starting from our next lesson, we will gradually introduce the operations of the NXMCD module through practical case studies. By examining different cases, you will learn how to use the MCD commands, gaining an understanding of and proficiency in mechatronic conceptual design. This will include learning how to achieve precise mapping between the virtual and the real, which will help you grasp the concept of product lifecycle management. Additionally, I aim to help you comprehend the design requirements related to the appearance and functionality of mechatronic products, fostering your innovative thinking skills. This will enhance your understanding of the collaborative needs between different disciplines, ultimately improving your teamwork capabilities and laying a solid foundation for your future careers. Please complete the following exercises. This concludes today's lesson. Thank you, everyone.